that we have gone through vector spaces and subspaces, it's time to look at the linear equations once more, now from a different perspective. Until now, what we did was look at the system of linear equations, equation by equation, which means row by row in our matrix equation. Now we're going to start looking at it column by column. And that happens to be the geometry of linear equations that we need in order to derive a lot of the algorithms that you know and love in machine learning. So let's get started. In some sense, the row picture lives in the coordinate space. Let me explain. When we say that an equation makes a line, what we necessarily mean is that an equation has solutions as a collection of points which look like a line. So that means a coordinate space, because it's in the coordinate space that you have points and lines and surfaces and stuff like that. Remember, vector space is just an abstract space of vectors with some associated properties of closure. So when we say Ax equal to B as a system of linear equations, and we start working with this system, equation by equation, we are basically going through the rows of the matrix equation. So it's a row picture. As you saw, equation manipulation was the same as Gaussian elimination, or row operations rather. It's in this coordinate space that you have each linear equation making a line or a plane in R3, for instance, and then you have intersections of multiple shapes. In R3, you might have 2 planes or 3 planes, and if you have 3 planes, then you have a point of intersection, which will be common to all the planes, and that points to a solution. Intersection of shapes would be a solution. If you have multiple intersection, infinity of intersections, for instance, if you have 2 planes that intersect in a line, then you might have a line of solutions if you had only 2 equations. If you had parallel lines or parallel planes, or planes that don't actually meet in a single point, then you may have inconsistency and you have no solution. All those things we saw multiple times, and we know algebraically how to handle it using Gaussian elimination, looking for inconsistencies, or if it is consistent, what to do. We know all those things. Moving on to the geometry that we will start working with in linear algebra, what it is saying is a completely different picture. So you have Ax equal to B as our system of linear equations. Instead of saying that these are multiple equations standing on top of each other, what we are saying is something very different. What we are saying is that Ax basically says a linear combination of the columns of A with weightages coming from this vector x. When that linear combination happens to equal B, the constants vector, that's when you have solution. If B is a linear combination of the columns of A, and if you can find the weighting factors required to make that linear combination, then you're done. You have the solution. The solution is just a set of coefficients of the right linear combination of the columns of A that will give you B. And this idea of visualizing B as a linear combination of the columns of A turns out to be a different kind of geometry, one that will give you a deeper insight. At this point, it may not be obvious to you why this is better or different really, but in about 10 minutes, I hope to convince you that this is the right thing to do. So let's take a look at our favorite equations. This one is in the coordinate space, so it's still the row picture. Just to start there, we had 2 equations, x plus y equal to 5, x minus y equal to 1, and they formed 2 lines in R2 as a coordinate space, and the intersection was the solution, which was right here. Now, if you look at the equations again and cast them in matrix form, you can see that A contains 2 columns, 1, 1, and 1 minus 1. That's because x plus y equal to 5 becomes 1, 1, 5. X minus y equal to 1 becomes 1, minus 1, and 1. This we know. Now, if you think of A as 2 columns standing side by side, A1 and A2, A1 being the red one and A2 being the blue one, then what this equation is saying is that the green constants 5, 1 as a vector is a linear combination of 1, 1 and 1 minus 1 with unknown weightages. So you just try to find the weightages and then you have the solution. How do you find the weightages? So that would mean that we start with these 2 vectors. These are columns of the matrix A, not the rows, not the row picture. Then we want to make some linear combination such that you get the green B vector. Let's try the geometric construction that we did much earlier. What we will do is to draw a line through the tip of B parallel to my blue vector. So that is going to be a blue dotted line. Then we extend the red vector the first column, all the way to this dotted line. Then we switch gears and draw a red line parallel to the red vector through the tip of the same constants vector b, and extend my blue vector now. So I have a bright red dotted vector and a bright blue dotted vector. And by construction, because of the parallelogram, you know that the diagonal going away from 0, the green vector, is the sum of this bright red dotted vector and the bright blue dotted vector. All we have to do is to find the scaling factors. How do you find the scaling factor? You just take the length of the bright red A prime, that is the extended red vector, divided by the length of A, the original vector, and that gives you the weightage that you need, x, to scale A1, and then similarly you find the weightage for A2. Now I have a plus or minus here. That is because if you had to extend the vector A1 not along the direction but opposite to the direction, then you would have to take negative sign. Same thing goes for the blue vector too. So that's how you find the weightages, and that's how you would get the solution. Now let's look at a different case that we dealt with in the row picture. That's when you had inconsistent equations, x plus y equal to 5, x plus y equal to, let's say, 1. These two lines representing these two equations in the coordinate space, they are parallel lines and they never meet, and so there's no common point of intersection, and the equations don't have a solution. How do you see that in the column picture? Again, we go back to our A matrix. This time I have 1, 1, 5, and then 1, 1, 1 coming from the second equation. And we're looking for x and y. That will give me my constants vector 5, 1 as before. So let's see what's going to happen. So I have my A1, the first column, and A2, the second column, red and blue respectively, and they are the same. As you can see, they're on top of each other. I'm drawing them slightly separated so that you can actually see them, but they are supposed to be on top of each other. Now let's try our construction. I draw a line through the tip of B parallel to my blue vector, and that is my blue dotted line, and then I try to extend my red vector to meet this line. As you can see, it will never meet that line because blue vector and red vector are parallel to each other, and this blue dotted line is a parallel line, so there's no solution. So this is how you see that there is no solution. Now, if you have a consistent system of equations, then you know that there is a solution. This is a bit hard to actually draw. The column picture is in 3D, and the columns now have 3 components because the 3 equations. Each column, remember, will have as many components as the number of rows in the matrix A. So that is a bit harder to visualize. So let's ignore that. What's actually more interesting is when you don't have a solution. So let's look at that one. If you have inconsistent equations in the coordinate picture, the idea was that you have no single point of intersection. The solution made something like a triangle here. Then we conjectured at that point that maybe the best possible solution might be somewhere inside a centroid or something, but we have no recipe really to find a solution. Let's look at the same thing in the column picture now. So our equations are x plus y equal to 5, 1, 1, 5, then 1 minus 1, 1, 1 minus 1, 1. But instead of taking 1, 1, 6, which would make it complicated to actually visualize, let's do a Gaussian elimination and take the equivalent thing, 0x plus 0y equal to 1. So 0, 0, 1. As you know, it'll have the same solution set because what we did was just Gaussian elimination. Let's see this picture. So what we have now is 1, 1, 0 and 1 minus 1, 0 as my red and blue vectors. And I'm actually going to show 3D here, but the 3D is kind of implicit. The z-axis is coming out of this screen toward me. So 3D is along this direction toward me from the screen. So let's draw the vectors. That is 1, 1, 0, 1 minus 1, 0, and the green vector is supposed to be 5, 1, 1. So green vector is not on the screen. It's actually jutting out of the screen a little bit, 1 unit toward me at the tip. That's hard to see when you're just looking at from the top. So let's kind of look at its shadow cast by light coming from me onto the screen. So that will be like a projection onto my screen. That looks like 5, 1, 0 because I'm just zeroing the z component, and that is the gray vector there. So that's not the vector we're trying to solve. We're trying to solve the constants vector, which is green. Now, what was our recipe? We draw a line through the tip of B parallel to my blue vector and try to extend the red vector all the way to that line. Now, blue dotted line is not on the xy plane, and my A vector is trying to extend itself on the xy plane, and it's never going to hit the blue line because it's not on that plane. It's actually sticking out. So that's the reason why there will not be a solution. But we drew a shadow of the green vector and the shadow of the blue line on the xy plane, which is the gray dotted line that you see there. So my A1 can extend to that dotted line. It's of course not the solution to this system, but it is actually something that is close to the solution. This is probably the best we can do. So there is a notion of the best possible solution or the best approximation to the solution coming out naturally from this idea that we can look at the shadow or the projection of the vector on the xy plane in this case. So let's continue. We draw a red dotted line through the tip of my green vector, and that again will not intersect with my extended blue vector because it's on a different plane. But the shadow of the red dotted line, which is shown again in gray, will intersect with my bright blue line. You can try to find the scaling factors by taking the norm of A1 prime dividing by the norm of A1 and the norm of A2 prime dividing by the norm of A2, and that will give you the scaling factor. But those numbers don't actually solve the system of linear equation that we started with, but that looks like the best possible approximation, which comes out kind of naturally from this picture. This picture is actually very simple, but this idea of using the projection as the vector that is the best thing you can have to be able to solve the system of equations is the one that is actually used in linear regression. So the machine learning algorithm of linear regression comes out of this exact argument. Of course, we need to learn a little bit more to see how you can actually project it in linear algebra, and also to what plane or what subspace you will project to. Those things we have to see. That will take a couple of more weeks, but we'll get there. And the idea is that linear regression comes out of this picture naturally. It's not something that is imposed by assuming that it's probably the centroid of some triangle somewhere or some hyper polygon somewhere. Not merely naturally, also when you actually do the calculation, you will see that it's very elegant. In a sense, the solution can be implemented by a couple of matrix multiplications and an inversion or something along those lines, which is computationally very efficient as well. So that is the reason really why we do the column picture. So we think of AX equal to B with M rows and N columns. If you look at that in the coordinate space in a row picture, you have M equations in N unknowns, and you know how to solve. But when you cannot solve, when you get inconsistency, you're kind of stuck. You don't really know how to proceed. But in the column picture, in the vector space, there will be a natural way to proceed and get to the best approximation to a potential solution. And that gives you a clear answer, a very efficient answer, and that turns out to be a machine learning algorithm. That is only the first one of many that you will come across in your life as a computer scientist, starting from this linear algebra background. That brings us to the end of this lecture. Next week, we will be looking at our toolkit to see what it is that we need so that we can do the projection and then understand where we need to project to, and then build our repertoire of algorithms starting with linear regression. So we shall see you in the next video.